In this video, I'm just going to go through some examples of truth tables and the various things we might do with them. So let's start with a truth table for a statement, and we want to know if the statement is a tautology, a self-contradictory statement, or a contingent statement. Let's start with the sentence A arrow in parentheses, A arrow A. And it helps to start reading these things off as what they mean. So for this I would read A implies that A implies A. There's only one simple sentence involved, so there are only two possible assignments, true or false. And now that I've set up the truth table, it's just a matter of going through and computing the values for the operators. So following my procedure of parentheses tilde, I start inside the parentheses, find the value of A implies A on each assignment. The rule for the arrow is it's only true when the left side is true and the right side is false. And in this case, my left side is A, my right side is also A. So that never happens, and I get true on both assignments. And the resulting value that I want to use for future reference is the value of the statement in parentheses, which I've written underneath the arrow. So I use that value as the right side along with the value of A on the left side to determine the value of the main operator of the sentence, which is the arrow outside parentheses. And on the first assignment, the left side's true and the right side's also true, so that makes the whole sentence true. Meanwhile, on the second assignment, the left side is false and the right side's true. That makes it true again. Remember, the only case that makes the arrow false is when the left side is true and the right side is false. So the result here is that I have a sentence that's true on every assignment, and it's a tautology. Let's take a look at a slightly more complex example. And when I say more complex, in fact, understand that these things don't really get more difficult. They only get longer. The rules for the operators are the same, no matter how long the sentence is, and the order of operations is the same. So if you can follow the order of operations and you know how to compute the truth value for each operator, this really doesn't get any more difficult than that. It just gets longer, and the only thing that can happen is that you basically your writing is bad and you misread something, or you're being sloppy and you don't have your columns and your rows lined up. So every single one really is as simple as what we just did at the heart of it. All the same, let's try a slightly longer one. And here we have the sentence, not K implies H if and only if it's not the case that either H or K. And it really is helpful to find a way to read these off as what they mean. If you're saying to yourself tilde K arrow H parentheses double arrow tilde parentheses H wedge K, and it means nothing to you, it becomes more difficult to assign the truth values. And if you are reading them off as what they mean, you can actually get to the point where you can predict ahead of time whether it's going to be tautology or self-contradictory. Sometimes you sort of develop your ear for the self-contradictory or the tautologous. So for example, on the right side of this horseshoe, it says it's not the case that H or K, neither H nor K, which means both H and K are false. So if both H and K are false, how could it also be that that's true if and only if not K implies H? That sounds like there's something wrong there, right? It sounds like that can't be, and so a self-contradictory statement is one that can't be. Let's see how this plays out on the truth table. We'll assign our values for H and K. I'm going to do alternating trues and falses for K, since I always start on the right, and we need 4 assignments. And I'll put the same values for K over on the where it appears at the beginning of the sentence, and then I'll alternate by 2's for H. Now the setup is complete, and I'm going to compute the values for the operators. Following the order of operations parentheses tilde, I can do either set of parentheses first, and I'll just start with the one on the left here. And before I can compute the arrow, I have to do the tilde, and so I'll put the opposite values to K, false, true, false, true. Now I want to make sure that I'm looking at those values as the left side of the arrow instead of the values for K. So the arrow rule is the only time it's false is when it's true on the left, false on the right. So that only happens on the last assignment, and the rest of them are true. Meanwhile, on the other side of the double arrow, we start inside the parentheses. The rule for wedge is that it's true as long as at least one side is true. So we only get false on the last assignment. And now we proceed to the negation on the other side of that. Let's remember to cross off the values for H and K. The negation applies to the result from inside the parentheses. So we get that it's false on all the assignments except for the last one, where the statement inside the parentheses is false. Now we can compute the values for the main operator, which is the double arrow in the middle, the triple bar. And the rule for the triple bar is that it's true when they're the same and false when they're different. So we get the result that they are different, 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 and different. So the sentence is false on every assignment. It's self-contradictory. Now let's try doing a truth table for a pair of sentences, and let's focus on the question, are they logically equivalent or not? There are other questions we can ask, whether they're consistent or inconsistent, and whether they are contradictory. Those were covered in the book, but I said we would focus on just logically equivalent. So let's just ask, are they logically equivalent or not? Let's compare the sentences not D or else B, and it's not the case that D and not B. I've got two simple sentences, D and B, so there's going to be 2 to the second power, or 4 possible assignments. And I'll start with B and alternate true, false, true, false. And of course, I'm keeping the values for B the same across the table. That is the whole point. Meanwhile, for D, I'm going to put 2 trues, 2 falses. Let's start with the sentence on the left, and we have a tilde and a wedge inside the same parenthetical group. The tilde comes first. So we'll do false, false, true, true. And then we use that as the left side of the wedge. The rule for wedge is it's true as long as at least one side is true. So we get true, false, true, true. That's the main operator for that sentence. And now moving to the sentence on the right, we go into the parentheses first, and inside those parentheses we have a tilde, so we start with that, and we get the values false, true, false, true. That becomes the right side of the dot statement, and the left side is D. And the rule for the dot is it's only true when both are true, so our values are false, true, false, false. And now the tilde is the main operator, and that applies to the result from inside the parentheses. And we just take the opposite, so we get true, false, true, true. And that completes our truth table. We've done the main operator on the left sentence, main operator on the right sentence, and we just compare them. And we're asking, in this case, are they logically equivalent? And that means the question is, are they the same on every assignment? So here we see that they are. True, false, true, true. Exact same value on every assignment. So they are logically equivalent.